And now it is my pleasure to introduce Jeannette Bohg, who is an assistant professor of computer science at Stanford University. And she was a group leader at the Autonomous Motion Department of the Max Planck Institute for Intelligent Systems until September 2017. And before joining the Max Planck Institute in January 2012, Jeannette was a PhD student at KTH in Stockholm. And she also studied at the Chalmers in Gothenburg and at the Technical University in Dresden, where she received her Master in Art and Technology and their Diploma in Computer Science, respectively. And Jeannette has received several awards, and most notably the 2019 ICRA Best Paper Award, the 2019 IEEE AS Early Career Award, and the 2017 IEEE RAL Best Paper Award. And her research focuses on perception and learning for autonomous robotic manipulation and grasping. So thanks for being here, and the floor is yours.
Thank you, Martina, for the kind introduction, and thank you for the invitation. Really appreciate it. And tell me if you don't see my slides, but I hope it works out.
Yep.
Yeah, so today I thought I'm going to talk about bridging topology and geometry and deformable object manipulation. And I specifically focus on linear deformable objects. These are hard enough, but I just want to give you a feel for why this is an important problem. So the ability to manipulate ropes and similar objects and tying knots with them has quite a few important applications in our lives. So when people are injured or are in surgeries, doctors need to stitch the wounds with medical sutures. And this is a basic skill for surgeons. And automating this step would allow the surgeons to focus on more challenging things and potentially save more people. Rescue workers heavily depend on ropes and metal rods to rescue people from high-risk environments. And we could put the Boston Dynamics robot, for example, or any kind of these walking robots in these high-risk jobs if the robots know how to use these ropes, for example. So let me first start with addressing like one particular problem, or focusing on one particular problem, which is the perception part of manipulating a rope. And here's a first example application that we want to achieve that I will use through the first part of this talk. So what we want to do is that given a goal image, we want to replicate it with a different whatever rope that you see. So here you have the robot basically starting from some rope that looks also completely differently from the one that the target image or the goal image is given. Then it basically brings it into the right shape. And so I will start with talking about how we achieve this. So first of all, this is quite a challenging task because there are lots of sources of uncertainty. So the sources of course, a rope has a very high dimensional state. And there's lots of sources of uncertainty coming just from perception for inferring that state from images. So there could be occlusions during manipulation. The rope could have varying appearances, and also the environment may have completely different looks. There might be clutter in the environment, and so on. So another source of uncertainty for this kind of task is in the dynamics of the rope. So it's actually quite hard to predict, not only quite hard, but also quite expensive to predict what a rope will exactly do or how it will deform once the robot grasps it and moves it around, right? So this is also very hard to model and introduces uncertainty in this process. But we want to achieve this task that I showed you before of bringing a rope that is in front of the robot into a particular goal shape that is shown to it in form of the image. And so that task, because there is so much uncertainty, requires continuous replanning and real-time feedback on the state of the rope with respect to the goal state. And so we use a state space representation of the rope. So basically the position of each of a number of points on this rope. And other people have used learned latent representation. We actually decided for the state-space representation because it allows for easier planning and easier inclusion of physics priors. And so this is really an overview of the approach here, where we assume we have some perception model that can give us this state space representation. And then this is fed into a dynamics model to basically optimize a sequence of actions for the robot to actually achieve that goal state. And so one of the main challenges, or one of the core challenges, as I mentioned, is how to robustly perceive this rope despite all the aforementioned challenges. And the main contribution of this particular work I'm going to talk about first in this talk is this perception system. And so what is at the core of this perception system is a differentiable renderer with self-supervising with a self-supervising objective function. So this renderer gets as input an image that you see here on the top. And the output of this perception network is, which I will actually not go in detail to, that one also has a bunch of contribution, but let's just say it's a perception network that takes the input image and outputs the state of this rope. So now we render this state in this simple grayscale image that you see here, denoted PUV. And given this rendered state, we can now form a mixture of Gaussians of the foreground and background model here, and then compute the weights for this, given the compute the weights for the new image or for the current image, given this Gaussian mixture model. So that's what you see here described as the PUV new. Okay. So now, using this rendered foreground background model and the foreground background model according to this GMM, we can now backpropagate and either adjust the rope state or fine-tune the network weights online, and then therefore basically come up with a better estimate of the rope state. And so what is important to note here is that this model doesn't assume anything about what specific color or appearance a rope has, or the background even has. This the only assumption, or the main assumption that we make here is that there is a good contrast between the foreground and the background color, but the actual parameters of the appearance are transient parameters that are captured in this GMM. Okay, so now here's a visualization of how well this method actually works. We just started with some qualitative examples using a manual initialization, and we compare our method that has this expectation maximization loss actually with an L2 loss that just looks at appearance in the image. And you can see from top to bottom an increasing, or actually from left to right, you can see an increasing amount of difficulty in terms of visual complexity of the scene. So the first row, you have like two examples where there's like basically just a rope on a uniformly colored table, more or less, and it works quite well. But then in the second loss, you already have the robot actually doing manipulation and therefore occluding parts of it, or you have an appearance that's actually split into red and green. You have examples where you have multiple ropes, where you have other distractor objects in there. And we also took like data sets here on the top right is like the data set from Berkeley that we haven't recorded ourselves, and our method works on this one. So this is just like a qualitative impression that I can give you of what this method can actually do. And one question I always get is like, can it handle intersection? And yes, it can, because we actually use a tracker. So a filtering method basically is underlying, and therefore can actually basically estimate the state of the rope online. And so what we get is essentially what I've already showed you before. So here again, we give the robot this goal image that is done with whatever rope. And then it has to bring this rope that is in front of it into the particular state. And what you see here, what is kind of interesting is that it really doesn't just attach the end effector to some point that it wants to move, but it uses the rope dynamics that are actually quite complex and under-actuated to achieve as much deformation towards the goal as possible, right? By not directly attaching itself to the points it wants to move, it actually uses the dynamics to get closer. Yeah, so, and also observe that the rope is being tracked while it's actually occluded and all of that, right? Okay, so this was kind of like just a brief outline of this work that we had published at ICRA 2020 and in RAL. And just to summarize the contributions of this work, basically the main insight that we use is that representing the problem in state space makes planning, especially, and including dynamics models, actually easier. For the algorithmic contribution, we proposed this differentiable renderer that I briefly showed you for self-supervised learning and robust state estimation. So we also didn't need any kind of hand-labeled data that was collected in the real world. This was done in a self-supervised manner. And the result you've seen is a system for manipulating deformable objects, or in this case, deformable linear objects into a given goal state. All right, so this is the work that basically solves, in a way, the perception problem for us of these deformable objects. And of course, it was still only doing the manipulation of a rope kind of in the 2D plane, and brought this rope into the shape, into this 2D shape in a way. So what we wanted to do next is really to do knots, like to basically have the robot perform knotting tasks, which are, of course, not only visually more complex, but specifically more complex in terms of planning and execution of this, of whatever the plan is. So again, like one of the challenges is that a rope is very high dimensional in both in state and in action spaces. We are actually, you could model, for example, by finite elements, and you could have like, I don't know, 100 degrees of freedoms, for example. It could be infinite, actually. On top of this, knot tying is more challenging than, for example, what I showed you before, because knots are abstract topological concepts, and there's no analytical function that really defines the distance of the current geometric state that a rope has to the final topological state that you want to achieve, right? So, for example, for these, if you consider the two rope states on the left, which function can tell us that the bottom one is closer to making the intersection shown on the right, right? Or, and I want to also mention here that this intersection, you know, is a representation of the topological state, not of the geometric state. So what makes things worse is that knot tying requires a long sequence of actions, and therefore motion planning needs to plan over a long horizon. And there's, of course, an exponentially large search space for finding the right plan. Right, as you see here. All right, so there is, of course, some related work that has already looked into this problem. Here's, for example, a work that applies sampling-based motion planning to knot tying. This work by Saha and Isto uses tree search, and they use knot theory to prune out unpromising branches, but we still found that it takes hours to just find a single plant. And a more recent work generates visual plans by embedding images into a plannable latent space using causal infogans. And the latent space has a simple dynamics model, and plans can be generated by A-star search. But the method has not really been demonstrated for knot tying. And also, again, like this is a latent representation, and it's harder to actually include more realistic dynamics into it. Okay, so an alternative way is to learn trajectories of knot tying by imitation. And this work by Vandenberg and Miller learns and improves human demonstrations for a particular knot. but the learned trajectories cannot be used for other initial thread configuration or a different knot. So it's kind of like hard to generalize. But the idea of using imitation learning is actually also quite interesting. So we propose a method that takes advantage of knot theory, sampling-based motion planning, as well as learning-based methods. So we can kind of take the best pieces of each of these works. And so knot theory helps us to compose knotting tasks into steps, as I will explain later. And each step is a topological action. And this decomposition makes each step shorter, thus easier to solve. And moreover, motion policies for each step can be reused for different knots. And in fact, when humans teach knots or knot tying skills, such as the instruction GIF on the right, we use very similar decomposition according to the topological plan. So, right, so this were just the points that I just made. And then we learn probabilistic motion policies for each step using reinforcement learning and imitation learning. And initializing the motion policies with imitating demonstrations helps bias exploration of reinforcement learning. And reinforcement learning allows unsupervised interaction on more diverse rope configuration and improves generalization on top of imitation learning. So at inference time, the motion policies for each topological step is used in a tree search to plan for the entire net. So we would always find a solution, although the learned policies are not necessarily perfect or failure-free. So here's an overview of the solution that we are proposing, and it has 3 levels. On the top level, we start from an untangled state, and the goal of the rope, as you see on the left side, and the goal topology is given. We decompose a knotting task into steps by searching for a path in this graph defined by topology. And on the second level, we use learned motion primitives for each of the steps. So the motion primitives take the geometric configuration of the rope as input and predict distributions of robot motion trajectories that accomplish the required topological changes. And then during planning, we validate the success of the predicted robot motion in simulation and to record the motion of the rope. And then on the bottom level, we try to produce the same rope motion on the real robot. And in this work that I just showed you before, we have developed a perception model that can estimate the geometric configurations of rope from images. And a neural network rope dynamics model that is 40 times faster than the simulator, which I had not talked about before, but I'm happy to talk about it later if anyone has questions on this. So we use this perception model in visual tracking and model predictive control, or the perception model we use in visual tracking, and then the neural network dynamics model we use within model predictive control to produce the desired rope motion and tie a knot. So our method is able to plan for an overhand knot within 1 or 2 minutes and execute the plan on a real robot. So here you basically see the setup that we have is just like the one before. And then here you see basically the motion plan that was generated. And on the top right, we show the RGB image to the robot. And in the middle is the estimated rope configuration. And the orange arrow is the action that is being executed. And the motion plan is adjusted between topological steps, as shown here, to improve robustness to the dynamics difference between simulation and the real robot, because the rope will not exactly do what you wanted it to do according to the plan. So we finally get this overhead knot. Okay, so with our method, the motion primitives trained by tying an overhand knot can be used to plan a pentagon-like knot from the overhand knot. In this example, the motion primitives find a motion plan within a few minutes, right? So this is this promising extrapolation that we were hoping to see. All right, so to explain the technical details now, we need to introduce the concept of topological states and topological actions. And the topological states describe self-intersections in the 2D projection of a rope. The order of encountering intersections while traversing the rope, as well as the vertical ordering of which segment is on top of the other, are recorded as the topological state. Okay, just like it's visualized here in this little animation. So topological states are abstractions on the geometric states of rope. And so imagine the geometric state space of the rope extends over the entire screen, right? And then topological states partition the continuous state space into these cells that you see here. And geometric states in each cell all have the same topological state. For example, this pair and this pair. And when we cross boundaries, intersections are being formed in the rope state or removed, which are basically these topological actions that we're trying to learn motion primitives for. So going back to the graph, in the system that I've shown before, we used, this is the graph we used on the first level of our proposed system. And the graph nodes correspond to the cells and edges. Edges are the topological actions connecting neighboring cells. The first level of topological planning tells us the cell we need to traverse and walk through. For example, we may need to travel from the light blue cell to the dark blue cell in order to go from an untangled state to this particular rope state that we want. Okay, cool. So now we have this plan. And in the second level, we want to find the robot motion trajectories for each of these topological actions that are conditioned on the geometry of the current geometry of the rope. And so in other words, we want to find a trajectory in this geometric state space, so the pink line here, that goes through the two cells and satisfies the kinematic constraints of the rope and the robot. So what we will do is we will learn a distribution of robot motion trajectories that can succeed at this desired topological action. And it has to be conditioned on the initial geometric state of the rope. We limit the space of robot motion trajectories to splines with 3 control points. One example here is shown in green on this rope. And the robot will grasp the rope at the first control point, move along the spline, and release the rope at the third control point. That's how we parameterize the actions. And the choice of letting the robot move along splines reduces long horizon RL problems to basically banded problems, and avoids instability issues with common RL algorithms that are more like feedback policies. And since there are many topological actions, we want to learn models that can generalize across those. And therefore, we define topological motion primitives as the function that takes as input the rope geometric state and the topological action parameters, and then it outputs a distribution over these splines. And so remember, the splines are the trajectories that the robot end effector has to follow for doing that topological action. So we designed a joint representation of rope geometric state and topological action parameters as input to the motion primitives. And the representation helps the motion primitives to learn similarities of motion trajectories we observed among human demonstrations of different topological actions. And it facilitates generalization across different topological actions. So I kind of have like 3 minutes left, as I see in my talk. So I'm afraid I may not be able to explain all the details of this. It's actually quite complex. But maybe I try. Let me first explain the categorization of the topological action and their parameterization. So there are 4 categories of topological actions. These are called Reidemeister moves. We just called them here R's. So it's like these Reidemeister moves 1, 2, 3, and then also a cross action. And within each categories, there are many different actions. And here are just some examples. And the 4 actions on the left are all R1 actions. The first parameter is all 0 here, which indexes which segment is used to form a new intersection. And the second parameter that is just highlighted right now is the direction of the new loop shown on the top. And the third parameter is the sign of the new intersection shown on the bottom. So whether it's on the top or on the bottom. And the two actions on the right are both cross actions, and they're like kind of similar parameterizations. So we exploit symmetries between different actions. And so one is spatial symmetry of the dynamics. So we can use this and reduce topological actions by just mirroring and all of these things. I don't want to go too much in detail. And the second type of similarities is in the locality of motion policies. Humans actually have a very specific strategy to do this. For example, they usually grasp the middle of a segment that will be on top and move towards the middle of the segment that will be underneath. And we basically encourage this kind of behavior also by having designed a specific neural network. And I think I just don't have the time to actually go through this. So it's pretty complex, but to encode this state. And I would just encourage you to check out the paper for more details. But basically, the output is this distribution of splines. And by using some geometric transformation in the three-part representation that I just showed you, we can learn to solve all the topological actions. Yeah, as you can see here, this is kind of like a nice visualization of how we group them together. And it's kind of slow. Let me see if I can speed this up. Wow. Mongyun, who made these slides, I just want to make a shout out to her, how much work she put into this. Okay, so we have like the 4 motion primitives that now encode many different topological actions, that also helps in planning. And I also have to let that play. Sorry for this. I can't speed this up. All right, so this is how we do the training. It's based basically on QTR, and we add basically an actor network because we found that CEM cross-entropy method is insufficient in the 60 action space that we are actually looking at, which is the spline space. And the actor network predicts this Gaussian distribution that initializes the CEM process. All right, so we train this also with demonstrations, and then we basically, for each motion primitive that is trained, we will chain them together according to this topological path that this research found, and fine tune them jointly. And by doing this, we encourage the motion primitives to generate motions that not only succeed at the current topological action, but also makes the next topological action easier in that plan. That turned out to be actually pretty important to do, right? So of these 3 different geometric options, the middle one is really preferred. And so then we do this tree search. As I told you, we are actually rolling out a bunch of options here, and maybe don't like a specific one because it's not really useful, and finally complete this tree search. So for experiments, we trained and evaluated 8 topological actions that are highlighted in this figure. And we just, I just want to show, like, these are the 2 hypotheses that we tested in our experiments. And one thing we found is basically that basically for unseen starred configurations, a naive baseline does really poorly. And imitation learning helps somewhat, but really combining these 2 and using RL to fine-tune the demonstrated trajectory makes a huge difference. We also evaluated whether the actor is actually useful, and it is. Big surprise, maybe. And then one thing that was also extremely important was to fine-tune each of the motion primitives through the entire sequence of the plan, because as I showed you, how well a motion primitives actually is executed depends on the geometric state it starts to. So it really depends on the prior motion primitives. So fine-tuning it within an end-to-end within an entire plan was really important. Okay, so to summarize, we approach this complex manipulation problem of knotting by first decomposing this complex knotting task into stages, and each stage will be easier to learn, and these stages can be composed to solve different knotting tasks. When learning for motion primitives for the topological actions, we observe similarities of motion policies from humans and facilitate learning of this similarity by designing the joint representation of the rope's geometric state and the topological action parameters. And for imitation learning and reinforcement learning, we use both actor and critic networks to improve the success rate. Joint fine-tuning of the topological motion primitives further improved search space. So thank you very much for your attention. I really would like to thank all my students, specifically these three who done this work, and I would also like to thank my funding sources.
Thanks a lot, Jeannette, for the really nice talk. And there is a question on Slido, and Naga is asking, how have the contacts been included in the model? Is there any minimum number of contacts that are needed to perform a knot? And how the number of contacts influences the action?
Mm-hmm. So I'm not 100% sure I know exactly what is meant by contact. I'm just going to assume here that this person means the number of intersections. Is that correct? I'm just going to answer it like this. I guess you cannot ask for a clarification. Yeah. So the number of intersections that we try to achieve with this method is basically coming from the goal knot, right? So you have a topological, you're given a goal knot, and that one has a topological concept. And so it has basically defined how many intersections there will need to be. And in principle, there is no limitation in our method that would say, oh, we can only do so many knots. What happens is basically that your tree search is going to be deeper, right? And but that will become more expensive the more intersections you have to form, so the more topological steps you have to make. The motion primitives themselves, they actually generalize to these different knots, as we have shown, right? Like we went from we basically went from a simpler knot to a more complex knot using the same motion primitives.
Okay, thanks. I guess that answered the question because we didn't get any clarification, so I think it's fine. And so I was just wondering, I have just one quick question. So it's mostly about the state representation. So in your work, you have an explicit state representation. So you're basically taking these key points on the rope. But I was wondering if you considered that this approach can be used also with different kind of objects. So for the rope, it's quite easy to imagine how to get this explicit state representation. But can this be applicable also with other kind of objects?
Yeah, that's a very good question. Maybe I can stop sharing also, but it's a very good question. And I'm thinking specifically just going to 2D pieces of cloth, right? And they're already, that kind of representation doesn't scale super well. So we haven't yet started working on this, but we are thought about maybe two different ways on how to move towards a more complex object than a linear object. And one would be to maybe just represent the contours of the 2D cloth, for example, instead of maybe the entire mesh. And the other one is to think about different resolutions of the mesh of a 2D cloth, right? Like, what do you really need in order to do folding, for example? Probably not as high resolution as necessary. But yeah, we haven't really further thought about this, or we don't have results yet, basically.
Okay, thanks. And I think we can discuss more in detail these aspects during the discussion round. So now we can move to the